All right, so this is the circular motion pre-lab. If you needed help, I'm going to, of course, try to give you my best tips for this. So for the sake of time, you can see that I set up a lot of the information. So at the top, here's the picture. The general idea is the puck and hanging mass are connected by a string, and the puck on top of the table is moving in a circle, so that's our main object in focus. And the bottom mass is basically hanging at rest. So it's at rest because we're assuming that this circle is staying the same shape, same circumference, same radius, which means this hanging mass and the rope do not move at all, okay? Some information was given to us, the mass that's hanging, and then the radius of the circular path and the time that it takes to complete one of these cycles. So right away, I actually identified the hanging mass first, which is an old idea, kind of the easy one. If it's not moving, it's at rest, staying at rest, the acceleration is 0, which means the forces need to add up to 0. So you can see I have an FBD here with things clearly labeled. This is the weight of the hanging mass, so make sure you don't get it confused with the puck's weight. And then, of course, tension is what's balancing it out. Great news for this, when I do set up Newton's first law for the hanging mass, which you want to extend this and add the forces that are present, you can on the side calculate the weight of the hanging mass because we know it's mass. All right, so after you finish this, long story short, what does it help you going to find? The tension, okay? So that was pretty straightforward, but again, the question we care about and the question it asks about is the puck. Okay, what's the mass of the puck? And we care about this because it's going in a circle, so that's our whole circular motion. Well, the puck then, if you look at the FBD from the side, vertically it's balanced because the table's normal force is balancing out its weight. And I did a subscript P here for puck. But horizontally, it's not balanced, which makes sense because it's going in a circle in the horizontal plane. So there should be an unbalanced force to make it accelerate. Just a little tip for kind of the pre-questions to this practice problem. I know that it's accelerating because it's going in a circle. And if you think of acceleration, its definition is change in velocity over time. Now, even though it's not speeding up or slowing down, velocity is not just about speed, it's also about the direction. So if either parts of those change, speed or direction, you have a change in velocity, which then of course means you have an acceleration. So since this is changing directions because it's going in a circle and it's curving around like that, I know that I have an acceleration from a change in velocity. We don't call this any type of acceleration though. When it's caused from a change in direction, we call it a centripetal acceleration. All right, and centripetal means center seeking, as a nice reminder. All right, so if it is accelerating, I'm going to continue the work right here. That definitely means that Newton's second law is in play. I'm going to add a subscript here, C, just because this is a centripetal acceleration, which, remember, total force and acceleration have a direct relationship. So if the acceleration is centripetal or center seeking, so is the net force. This is the puck that's accelerating, and again, there's a centripetal acceleration. So the question then was, what's the mass of the puck? Well, good news, my center seeking force at this location in time, because it does change as you go around, is the force in tension. And this tension is from the same string that was holding up the hanging mass, so this tension is the same as this one. So you can see why we did the hanging mass idea first. The problem is, though, I do now know the total force because there's only one, it's just the tension, but I don't know the centripetal acceleration. Well, this is where you got to think to the notes we did this morning. Centripetal acceleration, because the speed's constant but the direction's changing, it has its own unique equation, v squared over r. Good news with this, if you look at what I wrote up here, I said like, hey, we were given the radius and the time, but how does that help us out? Well, if we need centripetal acceleration to get the mass of the puck, you can see that the equation for it is v squared over r, and radius we do know. There's still one final issue though, the speed of the puck. I do need to know the speed of the puck to get this acceleration. Well, maybe then time is the final piece to the puzzle. Well, if an object's speed does not change, if it moves at a constant speed, the equation to solve for that is really just distance over time. Okay? But if you think about a circle and what the puck is doing, is the puck's traveling on the outside of the circle, which we call circumference. So instead of leaving this as just distance, if I'm talking about an object going around in a circle, the distance is traveling is the outside of the circle, which we call circumference, and the equation for that is 2 pi r. Good news, I can solve for the circumference because I know the radius, like we said earlier. But the final thing is you need to know the time it takes to go around the circle, which we do. And since it is specific to one time around, which we call the circumference, we actually write it as capital T because that's specific to the time of one cycle. So if you look at it now, I'm using Newton's second law to solve the mass of the puck. I know that the center-seeking force was tension, which I got from the hanging mass setup. And to get centripetal acceleration, I've kind of got to use these ideas which start at the end and work your way back up. If I solve for the speed by doing circumference over the time of a cycle, I can then take that speed and solve for the acceleration by doing speed squared over the radius. Once I have the acceleration, boom, you're home free. All right, hope this helps. Also, again, think about Newton's laws for those other questions that I asked. I did kind of explain what's going on with velocity, acceleration, and Newton's laws, but that's always our foundation. The FBD is an understanding, is it accelerating or not? No for the hanging mass, yes for the object going in a circle. That's always the foundation, so keep trying to think about acceleration and unbalanced or balanced forces. Good luck, everybody.